So in this video, we're going to walk through the process of deriving the formula for the derivative of the arc sine function or the inverse sine function. And we're going to be a little bit lengthy in this video because we're going to lay down some trigonometry review that's necessary for the derivation of that formula. So in the homework assignment that you are going to get that goes with this video, you're going to be given a summary of the derivatives of each of the 6 inverse trigonometric functions. And in this video, what we're going to do is go over why the derivative of the arc sine function is 1 over the square root of 1 minus x squared, and why we have this limited domain over which we're able to work. The process that we're going to use to show how to come up with this derivative is essentially the same process for each of the other functions. So in a typical class, we would go through and do all of them. For the purposes of an online class, I'm just going to do the first one and then identify to you that how we deal with the other ones is really the same process. The only thing that shows up that's a little bit of a glitch when you're doing derivatives of the inverse trigonometric functions is you wind up with this absolute value sign here. And this is simply because when we came up with, in trigonometry, when we come up with the formulas for the inverse trig functions, we're restricting the domain of the trigonometric functions to get one-to-one functions, and we have to be domain aware when we're finding the derivatives of inverse trigonometric functions. So we're going to focus on this one right here. So if you're interested in why the derivative looks like this video should hopefully answer that question. So the first thing that we need to do, if we're going to talk about the derivative of the inverse sine function, we need to talk about the sine function. So remember, the sine function looks like this. And the sine function didn't pass a horizontal line test in pre-calculus, so we knew that we couldn't find an inverse function for it. The inverse function didn't exist. So what we did in pre-calc is we said, hey, we are going to restrict the domain of the sine function and only let it run on the closed interval from negative pi over 2 to pi over 2 and throw away the rest of the sine function. And when we did that, we get this graph right here that clearly passes the horizontal line test, and which means that its reflection in the line y equal x is going to pass the vertical line test. So remember, if you have a graph of a function, to find the inverse function, you reflect in the line y equals x. So we restricted the domain of the sine function to run from negative pi over 2 to pi over 2. And over that restricted domain, the outputs ran from negative 1 to 1. So the domain of the restricted sine function was negative 1 to 1. And the range was negative 1 to 1, and the domain was negative pi over 2 to pi over 2. So to get the inverse sine function, we reflect this graph in the line y equals x. And when we do that, we get this picture. And so remember, when we're talking inverse functions, the domain becomes the range, and the range becomes the domain. So now the domain of the restricted function y equals arc sine of x, the domain is going to run from negative 1 to 1, that closed interval. And the range is going to be angles from negative pi over 2 to pi over 2, corresponding to the restricted domain that we imposed on the sine function to make it invertible. So this is an important piece right here. You can input into the arc sine function side ratios from negative 1 to 1. So remember, when we're working with the sine, if we have f of theta equals sine theta, we input angles, and the outputs are side ratios opposite over hypotenuse, or y over radius if we're working in the xy plane. It's okay to think of it this way, though. We have to be a little bit careful how we think about it if we're thinking in terms of opposite over hypotenuse, though. So anyways, this is what the graph of the arc sine function or inverse sine function looks like. And there's a couple things we want to notice right away. One, at the endpoints at negative 1 and 1, we have a discontinuity in the graph. So if y is equal to the arc sine, then we expect the derivative to only exist on the open interval from -1 to 1 because the derivative isn't going to exist where we have the discontinuities. So that's the first thing we want to notice. The second thing we want to notice is that any place where we draw in a tangent line on this graph, that tangent line is going to have a positive slope. So when we take the derivative, we're expecting the derivative to be greater than 0 just based off the graphical evidence that we see. So we expect the derivative to have a domain open interval from -1 to 1 and not exist at the discontinuities. And we expect the derivative values to be positive because the tangent line slopes, if we draw them in on the arc sine function, we can see that they are going to give us positive values. So once we've identified that, we're kind of ready to start to build the triangle that we need, the right triangle that we need in order to come up with the derivative of the arc sine function. So remember, on the if we are talking about the sine function, f of theta equals sine theta, we had to restrict that domain to -pi/2 to pi/2. So if we construct the triangle that goes with the sine function, we know that it's going to, between -pi/2 and pi/2, that triangle is going to live either in quadrant 1 or quadrant 4, because it's going to run between -pi/2 and pi/2. So if I draw that triangle in and construct it, it's going to live in one of those two quadrants. This is important because when we construct the triangle, we want to recognize that the base of the triangle will always be positive in those two quadrants, but the height, it's assigned height. So if we draw the picture into quadrant 4, we know that this value here is negative. And that's important consideration to keep in mind. So here's the way this plays out. If you start off with y equals the arc sine of x, and if you take the sine, right, this is a side ratio here. This is opposite over hypotenuse, and the output to the arc sine function is an angle. So if I take the sine of both sides, I get sine of y. Well, where does y live? Y is an element of this interval right here. So y is going to be an angle between -pi/2 and positive pi/2. And I get sine of y equals, when I take the sine of both sides, the sine cancels the arc sine and gives me an x. And x is going to be a side ratio between -1 and 1. It's going to be opposite over hypotenuse. And I can draw this x, I can write it over 1. X over 1 is still x. And that would make this opposite. And that would make the 1 hypotenuse. So I can construct this triangle either in quadrant 1 or 4. So to keep things simple, we'll just focus on quadrant 1. We know that y is an angle, so put y in as the angle. And if y is the angle, then x is the side opposite, and 1 is the hypotenuse. And the moment you do that, you can calculate the length of this side, which is just going to be the square root of the hypotenuse squared minus the side opposite squared. By the Pythagorean theorem, we know that the sum of the squares of the sides of a right triangle equal the square of the hypotenuse, and then we can use that to solve for that side length. So we wind up with this right triangle. This number is always going to be positive. This number is going to be either positive or negative, depending on whether we're in quadrants 1 or 4. And once we've constructed this triangle, we're ready to come up with the derivative of the arc sine function. So here's what we do. We want to find the derivative of the arc sine. So we start off with y equals the arc sine of x. We take the sine of both sides. So we get the sine of y equals x. And we construct the right triangle that goes with sine of y equaling x, which we did on the previous slide. So we construct this triangle. And from this triangle, we know that the sine of y is going to equal x, but we also know that the cosine of y is going to equal the square root of 1 minus x squared over 1, because the cosine of the angle y is going to be the side adjacent over the hypotenuse. And we know, because we're in quadrants 1 or 4, that the cosine is always going to be positive. This number is a positive number, regardless the quadrant we are working in on the restricted domain of the sine function. And once we do this, we're ready to go, because we can take the derivative of this. We can take d dx of both sides, And this is useful because we know how to take the derivative of the sine. We know that the derivative of sine is the cosine of y. But y is a function of x, so the chain rule or implicit differentiation says that we're going to need to multiply by the derivative of the inside function. So we employ the chain rule or implicit differentiation. We then take the derivative of x, which is just 1, and then to solve for y prime, which is what we're trying to figure out. What is y prime? What is the derivative of the arcsine function? We divide both sides by the cosine of y. We get 1 over the cosine of y. But we want to get back into x coordinate world, but the cosine of y by our triangle that we've constructed is just the square root of 1 minus x squared. And because this value is always positive, we don't need to worry about possibly implementing this absolute value symbol. So this number is always positive, which corresponds to what we were expecting by looking at the graph of the arcsine function. So there you have it. There is the derivative of the arcsine function, and it lives on a restricted domain from -1 to 1. Again, it doesn't exist at those discontinuities. And when we look at this, we can see, just based on what we have here in the denominator, we can't let x be plus or minus 1, or we would get a division by 0, which would be undefined.